Okay, cool. So I haven't recorded in a little bit, so I'm making sure that it is recording. Yeah, okay. So as I said, we are going to do the OSI model. And I guess, a good starting point is to kind of tell you what the different layers of the OSI model is. First of all, does anybody know what OSI actually stands for? So it's Open Systems Interconnection. So I had to actually write that down earlier because I wasn't very sure about the I part. So interconnections. Okay, so basically it's a model that is going to kind of give you an overview of how computers communicate on the internet, and there's different layers that allow this to happen, and there's 7 of them. So we got 7 layers, and let me know if like the tablet freezes or something like the other day. So let me just write down the layers first, and then we're going to talk about each of them. And hopefully by the end of this, you will get an idea of how all the layers work to basically have me speak on WebEx and you receive the video on WebEx on your end, and us be able to communicate on the internet. But it works not just for video, but pretty much for any sort of communication. So the first layer is application. After that, you get presentation layer. Then you get the session layer. Then you have transport. Then you got network. Then you have what's known as the data link layer. And finally, you have the physical layer. Okay? So let's start talking about these in order, basically. So when you have 2 computers, so you have, let's just kind of put a little drawing. So we have computer 1 and we have computer 2. And these computers are connected by some sort of cable. It could be like an Ethernet cable, or it could be a Wi-Fi connection, or it could be a coaxial connection. There's a lot of different ways that they could be connected, right? But the biggest question is, how do they talk to each other? Well, suppose that both of these computers are running the exact same OS. So let's say they're running Windows 10, and they have the same hardware, the exact same hardware. Like literally, they're just the 2 same models, and they're just connected. Okay, that might be easy to picture how that wouldn't be too hard to communicate, right? You just have to have some sort of protocol between them to be able to send and receive information, right? Okay, but unfortunately, that's not how the internet is set up, because we don't have all the exact same computer running. We have different computers. You might have this computer be a Macintosh, or it might actually be a phone, or it could be some kind of server, a Raspberry Pi, a video game console. It could even be an object like a refrigerator. You could literally have a refrigerator, with the IoT, which has a little, computer inside of it that is communicating via Wi-Fi to your computer, so you can set the temperature of the fridge, or a sprinkler system, or an AC, right? So the main issue is, how are you able to communicate between all of these things? It becomes a mess. Like, how do they all coordinate and talk to each other properly, right? And this is assuming that this is all on the same network, right? But what if I want to talk to the fridge in like a vacation home in the other side of the world? That makes it even harder, right? So the OSI model is kind of there to sort of allow a system to be able to communicate, and all the different stages to kind of make that system work. So going to the application layer is going to kind of be sort of the starting point of your communication, right? So for example, that could be something like Chrome or Firefox, or you're doing some sort of file transfer. You could also be doing some sort of web surfing. It could be some sort of email. It could be a terminal. And all of these have different sort of systems that they use that are part of the application layer. So for example, for file transfer, we have FTP. That's the file transfer protocol, right? For web surfing, we have things like HTTP and HTTPS. When you have emails, you have something like SMTP protocol. And for things like terminals, there's a lot of things. I mean, you could do Telnet. I don't know if SSH would kind of fit in here. I don't know if that would be really considered a protocol. But there's a lot of different protocols. But this is essentially what the application layer takes care of, okay? So the question is, how do all these different things communicate? Well, right now you're just in your local computer and you have your application running and you're using one of these protocols, right? What you need to do is you need to be able to send that information to the receiver of your information, to the endpoint. So what you do is you go to the presentation layer. What the presentation layer is going to do is it's going to take your information coming out of any of these and it's going to do what is known as a translation. Okay, so in a translation, let's say that you have some sort of email. Let's say you're sending an email or you're browsing a secure web page where you're putting in a password, things like that. So you might be putting your very secure password of password, or I guess password 1 makes it extra secure. And so you need to send this over the internet to the server. And so what you need to do is you need to translate this into the language of computers, which is going to be binary, right? So zeros and ones. You might also do fancy things like converting something from like ASCII to like EBCD1, which is I forgot. It's the fancy version, extended binary something, extended binary coded decimal interchange code. Yes. So that's EB.
In other words, IBM's that version of that.
Yeah, that's a good point. Talking about IBM, this is the other day. So yeah, so essentially you are doing this translation. In addition to doing the translation, other things that happen in the application layer are things like data compression. Why do we do data compression? Well, at least back in the day when the internet wasn't so fast and we were dealing with kilobits of information instead of megabytes and things like that, or megabits. Well, we had a very tiny, bottleneck that we kind of had to feed information. So it made sense to compress the information as much as possible. So, you could have things like lossy and lossless compression and things like that. One of the ways that you can do compression is potentially using hashing. So we can talk about a little bit about that with compression. But the easiest way to understand how compression works, if you don't know how compression works, is think about like a math formula. So if you have a line and you're trying to tell somebody that line in math, you could literally draw the line out and it would take a lot of little pixels to draw this line. Or you could come up with some math formula using probably like sine or forget the name, quadratic or other exponent to be able to generate a formula that can render that line. And if you did that, then the formula is going to take this much information versus taking the entire image, right? So using all these math formulas and things like that is a way to compress information. So anyway, that's the very, very simple way of data compression. But anyways, that's one of the things that happen here. And of course, with the password, you want to have some sort of encryption. And that is definitely hashing. So I'll show you like RSA later or whatnot. And then, of course, on the receiver end, there is going to be decryption, right? So that's pretty much what happens in the presentation layer. From there, we go to the session layer. So the session layer is kind of tricky. So that is going to be where your APIs typically tend to live. And so what the session layer does is, as the name implies, is it establishes a session or a connection between both computers, right? And so an example of that is, suppose you're browsing a website. And so the server, so you have the server over here, may contain, or there might actually be multiple servers, but they may contain different sections for things like images, video, and then text, maybe even somewhere where there's like sensitive information or some sort of database. Okay, so the job of the session layer is to establish a connection and potentially authenticate and authorize you access to the server, right? So if you're logging in, you're sending in your password over here, but then this needs to be, your computer needs to basically communicate here and then do some form of authentication. Authentication being, are you in, what is your username and password to be able to be authorized to access the information. So after the authentication, there's hopefully a authorization. Let me write that nicer, authorization. So you have that authorization to access. So like, let's say you're logging into Instagram, you put in your username and password, and then you're authorized. So that gives you access to the server, not the entire server, but only the parts that you're allowed to do, right? And so keeping track of what you can and can't access is part of your session. So we call that session management, at least as far as I know. And so, different sections of this are going to send you different parts. So you're going to get what is known as data packets from the server as part of your session, and some of those data packets are going to be text, and some of them are going to be image, and they're typically going to be separated. And then your browser is going to be, put them back together in the right order. So that's typically where your APIs come in, or NetBIOS as well. API standing for Application Protocol Interface, I think. Let me triple check. Application Programming Interface. But I mean, I'm sure you've heard of the word API before, like an API for an exchange, or for Twitter, or for things like that. So anyways, that's what the session layers do. It's establishing that communication and that authorization. From there, you kind of have the next two layers. I'll talk about them. They're kind of like very similar, but there are their own layers, and that's the transport and the network layer. Okay, so we have transport and network layer. And so with the transport and network layer, you have a couple of important things to take into consideration. And that is that when you're sending information, you can be sending a lot of information, or you could be sending a little bit of information, but it's still probably going to be information that needs to be split into tiny little pieces that we call segments to be able to send them properly. You can't just like dump information. I mean, I guess you can if you're using UDP, but you still want to decide what information goes where. So that's an important part of segmentation. What port number are you sending this information to? And then when you split the information into tiny pieces, you usually split them into sequences. Okay, so you have these segments. Just a lot of tiny little segments, and they typically contain some information, including the number of the sequence. So they all have, in fact, here, let me just, to make this prettier, we draw a big box, and then inside put the information. So we got the sequence number of that. You're going to have the port number where this is supposed to go, and then the data itself as well, or tiny pieces of the data. And so you're going to have a lot of these. Obviously, the sequence number will tell it which one goes before the other one, right? And so that segmentation is done in the transport layer, essentially. You also have what is known as flow control, which is very important, actually. I want to make sure that we understand that. So what is flow control? Okay, so suppose that we are talking between two computers. One of them is kind of like a home server, and the other one's your phone, okay? So we got your home PC, and then you got your mobile phone, and you're connected like a VPN or something, and you're accessing information from your home server on your phone, which it all boils down to, you're probably trying to watch like a home media, like you're at home, you have a copy of a movie and you're watching it in your phone just because you're fancy like that. Okay, so there's data flowing well, technically there's data flowing in this direction primarily, right? So you're trying to send to your phone the movie, okay, that you're streaming, or maybe you're transferring a file or something like that. But here's the thing: different machines have different bit rates or rates that you can send information or receive it, right? Your home might be using like a wire connection, unless you're using Starlink from space or something, but you're probably using a wire connection. And then that's that. You know, you have a decent connection. Let's say that it is maybe better, like gigabytes or something. Okay, so you got a gigabyte of this information. And however, though, on your phone you're using 4G or 5G. How much is 4G? What's the speed on 4G actually? Anybody know off the top of their heads? Let's see. Theoretical 4G speed. Around 100 megabits. Okay, so that's about 100 megabits per second. Now the question is, how much is the alleged 5G? Here, let's check that out really fast. 20 gigabits per second. That's yet to be seen, but that's actually pretty cool. But anyways, let's just say that we're living in 4G times, okay? So your phone is 10 times slower at potentially communicating than your home PC, okay? So you're transferring the movie or the files from your home computer to the phone, right? And so what happens, you know, if your phone talks to your home computer and it's like, hey, can you please send me this movie file? And your home computer is like, sure, let me just dump it on you. So it literally just sends 1,000 megabits per second of data to you. And here's the thing: your phone and the connection both can't really handle receiving that amount of information. So what's going to happen is that information is going to get lost. Okay? And this is, of course, going to be your transport layer, since that's the whole point of me talking about this. And so that's a problem, right? So your phone is going to respond and be like, yo, you know, calm down, like chill out and stop sending me all this information at once. I can only handle 100. So slow down. So what's going to happen is your server's going to be like, oh, okay, fine, sure. And it's going to send you 100 of this. So that is going to prevent data loss, essentially. And also basically overflowing your cache, you know, for receiving your buffer or whatever for receiving data, right? So that's one scenario that can happen. Now the opposite could happen. Suppose that you do upgrade to get this 5 giga, the 5G thing with the 20 gigabits per second. Okay? So your computer remembers. It's like, I don't forget. So the next time you ask it for a file, it sends it back to you again at 100 megabits per second. Because it's like, oh, it's this phone again, you know, with this 4G stuff and whatnot. And so your phone gets it and it's like, yo, I got 5G. I got 20 gigs. I can handle more speed. So send me all you can. And so now, okay, in this case, you're just like, okay, sure. If you want it, you'll get it. So it's going to send you as much as it can. Obviously, it can't go this fast, but it can go faster than what it was before, right? So in this case, it's optimizing the performance of the transportation, because it's like, hey, I can handle more. Send me more if you're able to. Of course, the server might not be able to, but if it can, it can. So like, you're downloading a video game update, you know, and you have better internet, then better speed than what you're really downloading at. Your computer is telling the server like, hey, I can handle faster. But the server's like, sorry, this is all I can give you. So that can happen as well. But in this scenario, but where the resources are good, if you can handle more, then the server's going to be like, yeah, sure, I'll give you more. And that's why, you know, when you're downloading a file, it'll typically download as fast as the server can give it to you, up to whatever your speed is, right? Or if your computer has a, you know, really old, it can only buffer so much information coming in, then I guess it would limit it to that. So that's kind of the purpose of the transport layer, is to sort of manage the performance and control flow. There's one more big thing about the transport layer, and that's going to be error control. So communication is awesome, but there is going to always be some flukes. And so the best way to handle flukes is to be able to detect them. If you send information and you're not able to detect a problem, that's the real problem, okay? So, You know, it's like, think about, since it's so popular right now, cryptocurrency, okay? So when you're sending money from one wallet to another wallet, the wallet is just a combination of alphanumeric digits or characters, right? It's one thing to say like, okay, I don't know your address, and another thing to send it to the wrong address, because then that crypto is gone. It is totally gone. You are screwed, and everybody's screwed. So it's one thing to have a mistake and know and fix it, and another thing to just send it and you don't even know that you sent it to the wrong address. So you keep sending it to the wrong address over and over again until you run out of money, right? So anyways, it's very important to detect errors. And so that's one of the big things about the transport layer, is to have that error detection. And the way you detect errors in computers is by what is known as check bits or checksum. Now, the concept between error bit detection is a little bit tricky. I was going to cover some of it in the computer organization, but I'll cover like a basic example of it, and then we can get a little bit more fancy with like double error correction. Or there's differences between. There are some algorithms that allow you to automatically correct one bit in error, and some that just tell you there's an error, but they can't correct it. So, for example, you might have a message that when you receive it, you do a computation on that message, and you can know if there's an error, as long as the error is limited to just one error. So, in other scenarios, there are other algorithms that allow you to not just detect that there's an error, but also automatically correct it as long as there's one error. There are also algorithms that allow you to correct two errors, but those take more space. Basically, the way you do it is you send extra bits of information. Let me give you a very basic example of something that you could do to avoid errors. I guess you could send the data twice, right? So if you're sending a package, now let's think about binaries. Let's say that we're sending information in binary of this form. We're sending these 4 bits, 1 0 1 0, okay? I guess one thing that you could do in theory is you could send the same thing twice, right? So you could send 8 bits instead of 4 and just send them in. And then if you notice an error between the first and the second 4, if they're not matching, then you know there's an error. You don't know what the correct thing is. You can't correct the error, but at least you know there is an error, right? However, if there's 2 errors, so let's say that you get really unlucky and both of these switch to 1, then you're not even going to detect the error, okay? So this is an example where you can detect 1 error as long as it's only 1 error. Now, probabilistically, you're not going to have more than 1 error usually, but this is an important thing. And it's so important that when people talk about what rate is, this is where this comes into play. Now, how do you actually do this, the whole checksum and whatnot? You use what's known as an XOR operation, which is exclusive OR. So, for example, let me give you a truth table here. And then exclusive OR means that if they're different, you get a 1. If it's the same, you get a 0. I believe that is the case. So essentially what this means is you're going to take all of the bits together and you're going to XOR them. And then you're going to store the result of the XOR as 1 extra bit that you append. So for example, if we got the 1 0 1 0, you're going to XOR them together and then store the result. So in this case, that would be a 1, right? Because you XOR 1 0, which gives you a 0. You XOR 1 0, which gives you a 0. You XOR both of those, which you get a sorry, you get a 0. I said 1, right? So you actually would append a 0 to this data. Let's just put it on the end, okay? So suppose that you send it over and one of these bits gets flipped. So let's say that it gets flipped to the 1. Okay? When you get it, you're going to perform the same XOR operation on the 4 bits here. So you're going to get 1 0 is going to give you a 0, and 1 1 is going to give you 0. I think I might have done with XORing wrong, and you guys didn't tell me. Yep. When I did the XOR of this, 1 0 gives you 1, not 0. And then 1 0 gives you 1 as well. And then putting those together gives you a 0. Like, that was okay anyways, but still, I didn't want to give you wrong information there. So anyways, now let's go ahead and get the error. So let's say that when we're transmitting this, it gets to the computer here, and you get a 1 0 1 1. This time around, when you do the XOR, you get a 1 for that, but then you get a 0 for that. And then when you XOR the 1 0 together, that gives you a 1, right? So you look at the check bit, and then you look at your XOR operation, and you can see that it's different. There you can detect there's an error. Now, why is this method better than the first method? Because this only requires one more bit, and the other one requires you to send the whole thing twice. However, it only detects one error. Again, if there's 2 errors, then the XOR operation might still give you okay, or there could also be an error in the check bit itself. And that's bad too, because like if you get a 1 there, so let's say that you get the right information, but the check bit's the one that's flipped, then you're gonna get like a thing that says there's an error in here, when in reality the error is in the check bit. So there's ways to do autocorrect in code. Again, I don't remember off the top of my head, but I have the notes on that to refresh myself, so we can go over that if you're interested. But this is just the very basics of how to do the error control. Okay, so that's kind of what is happening in the error correction part of the transportation layer. Is you want to have some sort of corrections, because errors do happen. There's hiccups in connections. There's solar flares. Believe it or not, those actually can cause errors. They're very, very rare though, except on one location. When you're on satellites, they happen more often. So those you actually do need to have more of this error correction stuff. Anyways, one more thing to do with the transport layer actually is the 2 protocols that they tend to use. Since I didn't mention that earlier, but I wanna make sure I'm explicit about it. We have UDP and we have TCP. So UDP is user datagram protocol, I think, and then TCP is transmission control protocol. Transmission control protocol, and then user datagram protocol. Is that right? Anybody can confirm that?
I believe you're right. User datagram protocol.
All right, thank you. Protocol. I'm gonna take my watch off. It's like doing weird things to the drawing. Okay, so the big difference between these, I'm sure most of you already know that, but if you don't, might as well point it out, is how they work, right? UDP is typically faster than TCP, which is why you would want to use UDP, but there's a big catch to this. When you're sending packets over the internet, one of the ways that you can sort of send information quickly is just to send it nonstop. Like, me talking to you is essentially UDP for the most part. I am just sending you information by talking nonstop, and I may or may not make mistakes. There may or may not be parts of me talking where like your internet hiccups and you might miss a word that I say, but you're not telling me every time I speak, you're not confirming that you received the right information. You're not sending me an acknowledgement package, ACK, okay? That is good for certain things such as streaming, where you don't care if there's a tiny little error. For games that require information to be sent fast, so like first-person shooters or multiplayer games that are like live, not like turn-based stuff. And it's good for that, you know, for fast things. Music, video, anything that doesn't require some sort of feedback. That's UDP, okay? So that's the fast one. However, sometimes it matters if the information you're sending is correct or not. In that case, TCP comes into play. So TCP is going to have these acknowledgments packages where you're sending information and then it provides feedback like, yes, I have received it, you know, we checked that everything's okay, that when I did the, you know, when I went ahead and did the error control, the package was good to go. You could still potentially do with UDP some sort of error control, but it would only be on the receiving end where like, you'll know if it's good or not but you won't know if like you won't be able to do anything even if it's wrong. Like you'll just be like, oh, it's wrong, but I can't ask for it again because it's UDP, right? So what is TCP good for? The internet, you know, FTP, where you're actually transferring a file, you know, with a file that actually matters, like especially if it's a compressed file, like a single bit that's messed up in a compressed file, like you would check with like a checksum or something, MB5, is going to totally break the file when you're trying to decompress it, you know, because like a formula where the number is wrong is going to give you a completely different result if you think about like the math example, right? So for streaming, UDP you can get away with, but things like files, emails, and things like that, browsing a web page and things, you really can't get around that, so you have to use TCP. Lag spikes are a common thing with TCP, and with UDP, when you miss something, if it comes too fast or you don't get it or anything, it's known as a packet loss. Okay, so in games you'll see things like, oh, I'm getting packet loss. That's problems with the connection, where UDP should send you stuff and you're not getting it, or something is happening, it's not arriving or something. Okay, so that's UDP and TCP, and that's kind of technically part of the transport layer as well. So where are we at? So we've gone through applications, present, session, and transport. And let's talk about the network layer. So the network layer kind of is part of the transport layer in a way. I mean, it is its own thing, but it's typically kind of talked about the same. So the transport layer is the one that's doing the segmentation part. The network layer is the one that's deciding how to kind of route things within the network. So for example, when you're handling things like IP, IP address, I believe, are going to be part of the network layer. So it's going to have your what is known as logical addressing and path determination. Okay, so let's talk about these things. So what is logical addressing? Logical addressing is basically figuring out in a network where you're sending information, like your phone number of the network. So that's your IP address, and also your mask as well. Now, it used to be IPv4 was the big thing, and those were like the IPs you would see. That would be something like some number there, then you probably have another 3 numbers there, up to 3 numbers there, and then I think 3 more numbers, and then 3 more numbers here potentially, I guess. But the range of numbers went from 0 to only 255 in each one. I think that was pretty much. I mean, actually, I don't think you would see an IP address starting with 0. And there were reserved ones for your local network, of course, with 192 to 168, and then the 2 more areas here. And then, of course, 255, 55, 255, it's kind of like a special one. So I suppose technically that would be 254 here in a range. But no, because the last digit could be 255, I suppose. But so essentially this addressing that is happening, that's part of your network layer. The way it happens is your packets contain not just a segment that you want, but they're gonna, once they're at your local network, while they're being sent, you have to put an IP address there so that it knows where to deliver it, right? So in the big internet, you have your packet coming in, and then there might be different computers in different places. So this might be like network 1. And somewhere else is network 2. And they both might be trying to communicate to the same server. So they're both accessing Facebook, okay? So Facebook needs to know to make sure to send it to the right one. You know, they establish the session and everything, but they need the IP address to know where to send it. So basically, you get the IP address, it arrives to the network, and then within the network, you need to be able to figure out where to send it, because a network might have multiple devices. You know, you have a computer 1, computer 2, you might have a mobile phone, another phone, you might have your refrigerator, as I said, etc., right? So the network needs to have an address as well to figure out where to go. That's part of your network address, and that's also your path determination as well. For example, this might be 192.168.1.5, and the other one's 192.168.1.8 or something, or 0 or whatever, right? So, and then the server itself has an IP address as well to be able to communicate with. So the packet itself is going to contain the mask and the IP addresses to be able to figure out where to send it, so that it doesn't send you the wrong person's packet, which would be a big security issue, right? I believe that is known as routing, but that might be a term that's a little bit too flexible to what it might mean. But I have it written down, so I thought I'd share it. Okay. So that's pretty much the network addresses. The big thing is being the path determination. Oh, with the path determination, actually, there's a couple of different sort of known ways to do that. There is open shortest path. There's border gateway protocol, and then there's intermediate system to intermediate system. And what these mean is, like, within the internet, think of it like a massive graph. How do we get from point A to point B, like within the world, you know? Are you going to like Australia, or are you going to like, I don't know, China, you know, like which way are you going, like across the water or something, right? And within like a local, you know, like a city network, you know, trying to go through the different parts of it to communicate between the two locations that you're sending and you're receiving from. So that path determination is part of this as well, to try to get you the fastest connection, but also save money, I guess, to the company that's, you know, Cox or whatever, I suppose, right? Because it has to go, you know, they might have bottlenecks in their nodes or things like that. So anyways, that's kind of like the network node. Next, you have the data link layer. Make sure, yeah, that's the data link layer. And then finally, you're gonna have the physical layer, okay? So you have your data packets from the network layer that they're coming in, and within, you know, the data link layer is going to have that logical addressing. While the network layer is going to have the logical addressing, the data link layer is going to have the physical addressing, okay? So let me write that down. So you have your network layer that has the logical addressing, so that's the IP address. And then you're going to have the physical addressing be part of the data link layer. Okay? Now, what is the physical addressing? That's the MAC address. Okay? So what's the MAC address? The MAC address is an address that is typically made of like, what is it, 12? I think it's 12 alphanumeric characters that are going to be split like 1A, 2B. I think they're hex. So I think they can only go from A through F. Or sorry, from 1 through F. So yeah, I'll Google that in a second. 2, 4, 6, 8.
Yeah, you're right. It's 6 octets.
6 octets. Okay. And then 1C. Okay, so 1, 2, 3, 4, 5, 6. There we go. So yeah. So essentially, these are I guess they're randomly generated by the manufacturers, but they're supposed to be hard coded to your hardware. So like you always have the same MAC address. No matter if you reformat the computer, you're supposed to have the same MAC address. However, that's not really a security thing because you can very easily change your MAC address. Like I think we saw that earlier in the semester, and if not, Google it and you'll find an application that will do it. I mean, this is one of the ways that you can get around like what is known as a hardware ID ban, like from a game. You just change your MAC address and that you no longer have that hardware ID, so it looks like you're a different computer. Piece of cake. So MAC addresses aren't necessarily a secure thing in terms of like, okay, you can't ever change it. So it's not like you're giving the social security number for life kind of thing. No, you're supposed to, but it's not really secure. But anyways, that MAC addressing is done in the data link layer. So what happens is you have these what are known as frames. So let's talk about that, frames, because frames kind of like an important thing. So you're getting your data packets, and those data packets have a couple of things. You have your segment, which we already talked about, where that contains. And then you also have the IP address of the receiver and the sender. And then you have your tail. Don't worry too much about that. But the big thing is that what you're going to get within your router typically is going to have those MAC addresses to know where to send things to as well. Okay? So you might have MAC address of 1, MAC address of 2. Those could also be, I guess, technically part of the package sent over the internet. I mean, again, like if you do a hardware ID ban, you could actually have that in there to make sure that there's still people working around that. But yeah, so in your frame, you're going to contain all this information, and you're going to be able to communicate thanks to that data link layer. Another important term that you're going to see when you're talking about data link layer is media. Media doesn't stand for like news media or like media like a DVD or music. Media just kind of stands for the information and the way that you're communicating, whether that is through some sort of optic cable, coaxial, or like radio via Wi-Fi or something. And so that communication that is happening, we call it kind of like the media, and you have the different devices that allow you to communicate. So you have your network cards, right? So that's a really poor representation of a network card, in like a little PCI slot or something. Okay, but basically you can access the media, so you can access these network cards by framing, and then the data link layer will control how the data is placed and received from the media. Okay, so you have that media access control. Also, the error detection that was earlier, that I talked about up here, that is happening in the transport. Your receiving computer has to do that error checking part, right? So that is done by your media as well. So that is done in the card. It's doing the check bit summing and seeing if there's an error, requesting to resend a package and things like that as well. So a kind of a complete way of how this framing works is if you have two computers, you have computer 1 and you have computer 2, okay? And so let's say that computer 1 and computer 2 want to communicate. So first of all, computer 1 is connected to network 1. And computer 2 is connected to network 2. And then these are connected via their internet providers. I mean, this could even go through satellite if necessary, but they're connected somehow. Okay? And so basically, you create your package. You got your tail, you got your error bits, everything. You have your IP packet. And so you send this to your network, and your network is going to go ahead and add more information to that packet, another head and tail along with the packet. It's going to send it over. Net 2 is going to receive it. It's going to add even more information to the beginning and the end to be able to know where to send it. And then it's going to send it to your card. And then from there, it's going to get rid of all the garbage, basically, and give you the real IP packet, which will then display the information here. Okay? The displaying part, though, is going to be the physical layer, I suppose. But that's important too. Okay. So again, your data link layer can be anything from like LAN cables, opticals, radios, and also the cards themselves as well. Another important thing with the data link layer to know is that it also helps to avoid collisions from multiple media trying to talk to the same source. So if you want to find more about that, I'm not really going to talk more about it, but that's like CSMA. And so, like suppose that two things are trying to connect to the same resource. It needs to be able to coordinate them and to control, what comes in and out to avoid basically confusing it. Everybody's trying to talk at the same time and kind of crash your own network, I suppose. It also controls how data is placed and received in the media, essentially. Okay, so again, it's monitoring. It's like internally, if you think of like how the RAM communicates with the CPU through the shoot, I forgot the name. I forgot the name of the cable. Not the cable, but the network. Anybody remember the name of the physical connection between like the RAM and the CPU, or the RAM and like the hard drive, the part of the motherboard? It starts, I think, with a B. Nothing from anyone? What do you call the pathway? I want to say buffer, but it's not buffer. It's the
Is it a bridge?
no, not bridge, but it's kind of like that.
The bus?
Bus. Yeah, the bus. Thank you, bus. Yeah, that's it. Yeah. So yeah, the bus is basically what allows all the communication between all the components of a computer, right? So the bus is the main bus. That is all the big sort of, well, not really, but like think of like the big wires that connect all pieces of the computer, and the bus is limited in the amount of information it can send and receive, right? So like the bus may get overcrowded if like the RAM, the CPU, the GPU, all these things are trying to communicate to the bus, and it needs to actually like control traffic in the bus. It's like a highway. So you can think of like the bus as one of the things that the layer is going to control here. The data link layer is going to control. It's like this imaginary bus that is your entire network. Okay? So yes, thank you, bus. See, I knew it started with a B, and I kept thinking buffer because BU, but yeah, thank you. I'm glad you remember that. So anyways, that finally brings us to the physical layer, which is the last layer. So the physical layer is just going to kind of be your endpoint, like your computer. I don't know what much more to say about it. I'm trying to think. Do I have anything here for that layer? See, the data link layer technically is like your switches and your Ethernet, and the physical is like the actual, I guess the coaxial cable could actually be more of the physical. So like the data link layer and the physical layer are kind of very sort of similar in what they are, but I guess properly the actual cabling and maybe like the hardware could be considered physical, and then the data link is more of like the frames, I would say. Okay, so yeah, you can just kind of think of those together. But all in all, you start out with your segment in your transport layer, and then you create your packet in your network layer, which becomes the frame in the data link layer, and that's pretty much what we have. So here, let me put that in. So you start with your segment. Well, actually, here, let's go to the beginning. So first of all, you're at your application, you're Googling Chrome, or you're gonna do some FTP thing, and then you have your presentation, right? So let's just kind of scroll down as we go through this. So you have your application, your presentation is going to be where you translate, you encrypt the data, you know, you're sending your email, you go ahead and you encrypt it, you compress it and whatnot. You establish that, make sure you have your established connection between you and the server. So you log in, you authenticate, you're authorized, and then you finally are going to go ahead and create your segment in the network layer. So you have your little packet that you're going to make. Not the packet yet, but just the data itself, okay? You're going to figure out how much data you're going to send. You're going to generate potentially some error-controlled, you know, bits, checksum bits and whatnot. You're going to decide, finally, on the network layer, where you're sending the information to. So you're going to have your source IP and your destination IP, along with the segment that you just made up there. To that, you're going to go ahead and you're going to add the frame information. So you're going to add the source MAC address, the destination MAC address, any other information, FCS and all whatnot. So that finally brings us to actually having what we send over. Then we have it on the, you know, on the physical wiring and whatnot. And then you kind of go backwards when you receive it. So you have to kind of strip the packet and then figure out where this came from the source IP, change the segment back, you know, decrypt it and whatnot, and then you have the data. So it kind of goes in like a circle. Actually, it's more of like going this way, like a wave. Okay? So again, you have your segment, and from there, you create your package out of that by putting the IP addresses, the source and destination. From that, you're going to throw in your MAC addresses as well. Now you have your frame, and yeah, that's pretty much it. So, any questions? Cool. Well, that was pretty much an hour long. So, well, if there are no questions, then I guess we can move on. Oh, Chris is here. So, yay. 2, 4. So we got everybody right now. Great. Either way, I recorded it. Well, I'll stop the recording anyways, and I'll upload that. That way, the content that you missed. That's fine. I'm recording, so I'm just going to stop the recording now, and then I'll upload it. So if you missed the beginning, you can watch it later. So, for those who... Cool. Well, thanks for watching on YouTube.